G'day. So far, when we've been completing our first sets of lessons and activities in physics, we've been focusing on motion which is working in a single dimension, either backwards or forwards or up or down or something like that. Here in this video, we're going to start looking at motion in a plane, in other words, motion that exists in two dimensions, and represent that motion using vectors. For syllabus content, we are doing the second part of Module 1 Kinematics. The second inquiry question asks, how is the motion of an object that changes its direction of movement on a plane described? So when we're talking about a plane, we are talking about motion in two dimensions. So say our x-axis and y-axis that you might be familiar with, say in a graph, that is one example of a plane. We're looking at motion simply in two dimensions, not introducing the third yet. Now, content statements 1, 2, and 3 are all quite similar by nature. Roughly all of them are saying that you need to have an understanding of how to analyze vectors, draw vectors, calculate with vectors when they are in two dimensions. So our learning intentions today, first off, is to be able to combine two vectors using addition and subtraction methods. Once we do combine two vectors and end up drawing what we call a resultant, you'll see that the vectors and the resultant form essentially a triangle. Because we are working with triangles, the application of trigonometry techniques are quite useful to us to be able to then calculate things about our unknown or resultant vector, these being magnitude and direction. We'll then just have a little bit of a review of scenarios when you may want to use addition or subtraction methods. And then at the end, we'll also be resolving a vector into its x and y axis components. Essentially, it's the reverse of what we're going to be learning in the addition and subtraction part of this video. It'll make a little bit more sense visually what resolving a vector in x and y components means when I actually show you that at the end. So first off, vector addition. When we add two vectors, we always take our first vector and add it to another. So it could be something like this. When we add two vectors together, especially when they're going in different directions, we use what we call the head to tail method to combine those vectors together and figure out what the resultant vector is, the vector at the end, when we put those two beginning vectors together. So what I would do here with the head to tail method is draw my first vector, and at the head of the first vector, we're going to start drawing the tail of the second vector, and it will look something like this. So first plus the second. What we can then do is take the tail of the first and connect it up to the head of the second, and this is what we call our resultant vector. A simple example to describe the vectors that are here in front of us may be something along the lines of having a person walk north and then walk east. This resultant vector here is reflective of displacement. So instead of showing the actual path taken, this is the straight line path here. That should be a little bit reminiscent from some of the content we covered a couple of weeks ago. Effectively, what we have here at the bottom of the vector is the starting point, the origin, and the end point here of the vector is also the place where the person has stopped traveling after moving east. Something to note when adding vectors, unlike numbers, is that the order in which we add is important, because when we use a head to tail method, let's say we went east first and then north to follow. Once you've got a little bit of practice, adding vectors together is actually quite a simple process, as long as you're making sure that you're adding, again, the first to the second and drawing an arrow to connect the starting point to the end point of the two vectors, that being our resultant. Vector subtraction is a little bit trickier, but there is a trick to make the way that we combine vectors together quite consistent. So if we generally subtract one thing from another, we can always recognize that that is the same as adding a negative version of the second number. So here, if I subtract by V2, really I can say that I am adding negative V2. That's what this little equation is showing us here. And using that information can be quite helpful when undergoing some sort of vector subtraction. So in this first example, we're going to use north and east again. We're going to have an up arrow representing our north direction, and we're going to be subtracting in the east direction. Now, we're not going to end up with the same resultant as we did for addition. In fact, in a lot of ways, the result that we're going to get is opposite. And that should be expected because we are undertaking a subtraction. So what I'm going to do first is show here that if we subtract V2, that really that's the same as adding negative V2. So looking at this vector here, the negative version, let's just say that this is v2, this is v1. What we can do is draw up negative v2, which would be this. So it is v2, but with the same size vector, but pointing in the opposite direction, meaning that we can write v1 minus v2 graphically in a similar way, but instead show it as an addition where we are adding the negative version of v2. So that is here. When we do that, all we need to do is use the same addition rules using the head to tail method to resolve the two vectors and find what the resultant is. So that would mean that I would draw vector 1 first, and then negative v2 second. And our resultant still goes from our starting point to our endpoint on the two vectors. So we'd start here and end up going to that same endpoint, and that is here v1 minus v2, or our resultant. What we can then do once we have our resultant is use some simple trigonometry to be able to then determine magnitude and direction. So in this example that I've already drawn up for the sake of efficiency, we have two vectors, one 4 meters south or down, the other one 6 meters right, or we could also call that east. What I've then done is use our vector addition strategy, drawn out the resultant, and what we then can do is use again trigonometry to then find magnitude and direction. The first thing I've done is found magnitude. That's actually quite simple. We can use Pythagoras' theorem because we already have two side lengths that are known and one that is unknown. Something to note too, because of the direction of the vectors that we have, one going due south and one going due east, we can assume that this triangle has a right angle, meaning that we can use things like Pythagoras' theorem and right angle trig like SOHCAHTOA, which we're about to do in a second. So the working here for finding the actual displacement or vector S, the magnitude of it anyway, is quite simple. All we need to do is run through and apply Pythagoras' theorem as shown in the working. Reporting the direction, however, is a little bit trickier, and that's all these steps included to the left. There are two ways that we can show the direction of a vector. We can either use a true bearing, or we can use a bearing notation that includes north, south, east, west notation. Now, true bearings are fairly straightforward. We always say that the north direction is representative of 0 degrees. And depending on where our vector is pointing, depends on what degree we give it. Now, it could be anything from 0 to 360 as we move around, but what we need to do is look at where the vector is pointing. So let's say it was pointing in this direction. What we can see here is that the angle between north and where the vector actually goes is 135 degrees. So that would be the angle or the true bearing that we would report. This north, south, east, west notation is a little bit simpler in some ways, a little bit more complex in others. What we do when we're using this north, south, east, west notation is always reporting whether or not the vector is pointing in a northerly or southerly direction first, and then indicating the number of degrees away from that north or south point, either in the west or easterly direction. So for example, this bearing here is north 45 degrees east, meaning that the vector is pointing in the northerly direction, it's in this top half, and that the bearing is 45 degrees east of our north mark. The opposite to that is south 45 degrees west. So the vector is in the southerly section of our cardinal points, and it is 45 degrees west of our south point, and that's the second bit there, 45 degrees west. Both bearings are acceptable as long as you are using them correctly. Obviously, if you're being asked to use a particular notation, you should always go and use that. In this example here, our true bearing is not actually in the triangle itself, but if we were to calculate the angle here at the top of the triangle, because we can extend a line out north in the northerly direction, and one of our vectors is going south, means that the angle inside the triangle plus the actual bearing itself, or at least the true bearing, is equal to 180 degrees. So by using our simple right angle trigonometry, I use tan theta in this example. You could have used sine, cos, or tan because we know all of the side lengths. But we're able to use that right angle trig to calculate the unknown angle, From there, we can find the true bearing by doing 180 degrees minus, in this case, 56, the angle inside the triangle. Now, depending on where the triangle is relative to where the direction of north is and where, etc., calculating the true bearing can be really simple. Sometimes it's just a matter of calculating an angle inside the triangle. Other times it's a little bit trickier and you may need to use some simple geometry and angle techniques to be able to find it, just like we did in this one, by knowing that the angle sum of a straight line is 180 degrees. Now, if we were to report a final answer for this question, we could say that we have a bearing of 7 meters. That's to one significant figure, but the bearing itself is 124 degrees true. An alternate direction that we could also give is south 56 degrees east. And again, either one of those directions or bearings would be acceptable to go with that 7 meters to describe the vector that we have here. So a big question is, when do we use vector addition and subtraction? Essentially, we use addition when we're trying to find the result or combination of two or more vectors. A great example is always displacement. So if a person walks 20 meters north and 30 meters east, we can use vector addition to find their displacement. And that comes from the general principle that one thing plus another, so displacement 1 plus displacement 2 leads to displacement total. When undertaking subtraction, we generally try to find the change of two or more variables. That is effectively what subtraction is able to calculate. So we should already be familiar that delta V is equal to V1 minus V2 or V final minus V initial, however you want to represent it. But delta V is the change into velocities. So we should already be familiar with this idea of change in velocity. That's a lot of the time where we would use vector subtraction in particular. But yeah, delta V or change in velocity is always equal to velocity 1 minus velocity 2. Generally, that means final minus initial. But we can use, again, another way of representing or writing delta V, and we could write delta V is vector 1 plus negative vector 2. And that can be a way to graphically resolve a lot of these change in velocity questions where we have vectors going in different directions. An example question that we could do is that a boat is traveling at 25 meters per second north. Just notice a typo there. I'm just going to do a little correction, but it's 25 meters per second north, and then it changes direction. It then travels at 20 meters per second west. And if we were to be asked to calculate the change in velocity of the boat, what we should do is take vector 1, which is at 25 meters per second north, and add to it negative of vector 2. Last quick thing that I'm going to show you is that we can also resolve a vector into x and y components. So for example, if I had a vector like this, that's going in a roughly southwest direction, sometimes it can be necessary to actually turn our vector into an x part and a y part. So what I can do here is draw out essentially a line that goes straight down. You could also do alternately straight up, but we want it in line with the bottom of the vector there. Similarly, we can draw a dotted line that goes across the vector. This is going to be completely horizontal, meaning that we now have a set of perpendicular lines. Again, they are technically imaginary, but they do represent the vector for the y component and the vector for the x component. This is something that I'm just introducing today. In terms of application, it's something that we're going to be working towards in future lessons. Thanks everyone. In the next video, we're going to begin to tackle some simple problems and calculations that we need to solve for different types of two-dimensional motion. So lots of worked examples in that one. I'll see you then.